Now, we are going to go to the topic of complex integration. Remember, we are doing the calculus of complex valued functions. We have done complex differentiation, limits and continuity, differentiability. Now we're going on to discuss complex integration. And this, you have to learn the technique here because it's not as straightforward as working with real valued functions. So firstly, let me give a definition of what we mean by the integral of a complex function. As I said, I'm no longer in the realm of, what was an integral? In first year, an integral of a function was the area underneath the curve. Then in second year, you also came across a line integral. Actually, these are line integrals. These are pairs of line integrals. So they're not areas, but you can interpret them as pairs of line integrals. So if you take a function f of z, dz, the integral of that, you have to integrate along a path, gamma. Gamma. You integrate along a path, like a line integral along a path. So this is defined to be the integral of u plus iv dx plus I dy along the path gamma. That's the function, and that's the differential. Those are the differentials, including a complex thing as well. Yeah. If I were to multiply this guy out, I would get what? U dx plus I v dx plus I u dy, and then I squared is minus 1, so it's minus v dy. And if I were to rearrange this in the shape of real and complex parts, the u dx and the minus v dy go together, plus I v dx plus u dy go together. So that's the definition of a complex valued function. It's a sum of two line integrals. So it's an integral on a path, or integral over a path. Path gamma. The path could be any path. It could be a straight line, it could be a circle, a piece of a hyperbola, or a parabola, whatever it is. Any kind of a path. So, to simplify, we can use what we call a parametric representation. Parametric representation. In other words, instead of working with x and y, we can express each of x and y in terms of a third guy. Let's call him t. So we can have x of t and y of t. So both guys are related to some common guy. Instead of being related to each other directly, we now connect them via a third guy, t. That's really a parameter. So then a function can be written as z equals to x of t plus I y of t. And if I take dz dt, it'll be dx dt plus I dy dt. Or I can write the differential of dz is dx dt plus I dy dt. I've just taken the dt across. This dt is there. That's all. That's like a derivative of that volume, that area element, basically. Let's take an example. How does it work in practice? There are lots of examples in the tutorials that will help you to practice. Let's take an example. I'm going to take this one in the textbook because I'll do it in two different ways. You get the same answer, so we'll just corroborate that they are the same thing. Find the integral along a path gamma of 2z plus z bar dz, where gamma is a semicircle centered at 0, 0, and radius equals 1. In the upper half plane, we have to say lots of stuff here. And one more thing I have to say is that we are doing this counterclockwise or anti-clockwise. Direction is important here. So we have to say lots about the function. We have to precisely say what the path is. So we close all loopholes. Draw a picture. I mean, what we mean is this. So we have a semicircular path, upper half plane, you can see, top half of the semicircle. And also we are saying that it's anti-clockwise. It's going opposite to the direction of the clock. Okay, so now we need to integrate that line integral over this path. If we were doing like a surface integral or a line integral, the meaning could be like you have a certain path. Okay, you have like a big sheet on the top. Imagine like a marquee, a big tent on the top. And you want to find, if you take a piece of curve at the bottom, any curve at the bottom, and you project this curve onto the marquee, it'll map out some curve on the top, on the marquee. Not the same as curve itself. Right? What is the area underneath that curve? That's really the question. This curve I draw on the floor is projected onto the marquee on top. What is the area of that slice directly below? That's really the integral we're trying to calculate there. But now, as I said, there's two line integrals here. But I'm just giving you a naive interpretation of what this means. So, what's the equation of a circle, guys? Of radius 1. You can say it's x squared plus y squared equals 1. But it would be prudent here to use a parametric representation. What's a parametric representation of a circle in terms of some parameter t? You may say, well, let y be t. Then x will be the square root of 1 minus t squared. That's a possibility. It's not a very useful and clever possibility. A more intelligent possibility is to say, anyone knows? What's a more intelligent way of parameterizing a circle? Sine and cosine, right? You can say let x be cos t and y equals to sine t. Then x squared plus y squared is indeed 1. So you can see, of course, x squared plus y squared will give you 1. Sine squared plus cos squared is indeed 1. That's a possible parameterization of a circle. The function z is x plus iy, so it's cos t plus I sine t. Okay. Or you may write this as e to the it. I'm going to actually use this method here at this stage. And of course, z bar will be e to the minus it. It's a conjugate. So it will be for cos t minus I sine. Or e to the minus I. That's Euler's theorem. E to the I theta is cos theta plus I sine theta. How about dz? Dz, differentiate this guy, minus sine t. There's two ways to write it. You write this as minus sine t plus I cos t dt. Or I can write dz is differentiate this guy here. What's the derivative of e to the? Oh, I circled the wrong one. I meant this guy. dz. Differentiate e to the it, man. It'll be e to the it, and the derivative of the inner function, which is I. Is I e to the it. dt. Now let me compute the integral. The question was to find integral along gamma of 2z plus bar z dz. Let's do that. That is the integral of 2z. Well, z is e to the it, so it's 2e to the it. Plus z bar is e to the minus it. And dz is I e to the it. Right, now one of the other things we need to do here is settle what are the limits of the integration. We are saying that we are dealing with a circle, starting from here and going to there. In other words, it ends, starts walking from here and walks along the circle and ends up there. So I need to know what are the limits on t. The parameter t is like the angle here. So where does t start? T equals 0. And ends up at t equals 5. T goes from 0 to 5. So you can say 0 less than equal to t less than equal to 5. That's the thing that you have to work out. So then the limits are 0 to 5. Because now we're dealing with t, no more z. We converted the z into a parametric form in terms of t. And now I just hit this with the normal integral. Well, firstly, let me simplify this. Multiply this out. 2, so it'll be 2i e to the 2i it. Plus, multiply this here, it'll become plus I et. Oh yeah, that's right. I thought I had something wrong. That's fine. So if you want, you can take out I as a common factor, 0 to pi, just to make it look simpler. 2e to the 2it plus 1 dt. Now I integrate as normal. How do you integrate e to the 2it? It will be 2e to the 2it divided by 2i. How do you integrate 1? It's just t from 0 to pi. Derivative of e to something will be e to the something divided by the derivative of the inner function. It's 2i. So then this thing cancels off, 2's cancel off. We'll come back to this I story at the end. Firstly, let's put the pi in. E to the 2 pi I over I plus pi minus. Now let's put the 0 in there. E to the 0 is 1 over I plus 0. I'm just applying the fundamental theorem of integral calculus. Substitute the limits here and subtract them. First put in pi, e to the 2 pi I upon I. Plus, put the pi there as pi. Subtract, then you substitute 0. E to the 0 is 1, not 0. 1 over I plus 0. Right, so let's see if we can get this right now. So this becomes I into. What can you say about e to the 2 pi I? E to the 2 pi I, you should know the answer without working it out. But if you want to work it out, it's cos 2 pi plus I sine 2 pi. Using Euler's theorem. Cos 2 pi is 1. Sine 2 pi is 0. So it's 1 over I. Plus pi minus 1 over I. So then these two guys kill each other. And you get the answer I pi. Notice the answer is it need not be. It could sometimes be a real value function. But I'm glad it's complex because you can't give you the specific diagram thing. You can't draw a picture. This area is pi I. What is pi I? I mean, an area of pi is understandable. real number. What is pi I? You see, these are mathematical objects, and if you learn the process and how the mathematics works, it's building up to a bigger game in future. I know what you're thinking now. What are you thinking? So I went with this route here. You're probably wondering, what happens if I went to that route? What if I use cos t plus I sine t? Would I get the same answer? Normally, I'll just leave you to try this out yourself at home, but let's work through it. So you can practice the mechanics of the integration and stuff. We'll come back to you. Are you ready? Can we move on from this slide? That's a typical kind of problem now. You get an exam or test. Calculate a certain integral along this path. Then you must parameterize the path, work out the dz, plug it into the original stuff, churn out the integral. That's how it works. Any questions? Anything that's not clear at this time? As I said, there are two options. You can either go with this blue line, which I've done there, or you can go with this line, which I'll do now. Practice some integration. Right, let's repeat that same problem. Repeat with z equals to, what is it, cos t plus I sine t. The dz will be minus sine t plus I cos t dt. The parameters are the same, 0 less than equal to t less than equal to pi, because t is the same. It's the same parameterization. So then we are doing integral along gamma of 2z plus z bar dz. Oh, by the way, z bar would be cos t minus I sine t. So this is not to pi. 2z will be 2 cos t plus 2I sine t plus z bar will be cos t minus I sine t. dz is minus sine t plus I cos t dt. Become quite long, right? And you're probably trembling in your boots there because you're thinking, we have to multiply all the sines and cosines and then integrate it. In case you're wondering that, you're absolutely right. I have no solace for you. That's what we have to do here. We can simplify it a bit. 0 to pi. Let's collect some terms. So 2 cos t, 1 cos t. So that's 3 cos t. 2I sine t minus I sine t. So it's plus I sine t. Multiplied by minus sine t plus I cos t t. It's a little shorter now. Let's multiply this out. 3 cos t times minus sine t is minus 3 sine t cos t minus I sine squared t plus 3I cos squared t. Then I times I is I squared, that's minus 1 sine t cos t dt. Right, so now, oh, where's the I? This should be a 3I. 3I cos squared t. Let me group the real and imaginary parts together. This becomes integral from 0 to pi minus 3 sine t cos t, that's minus 4 sine t cos t, minus I. This will be sine squared t minus 3 cos squared t. Just keep a very careful eye on what's going on here, because it's easy to make mistakes. So now you've got to integrate this. I think what we should do is 0 to pi. This minus 4 sine t cos t. We can exploit the double angle formula here. 2 sine x cos x is sine 2x. So I can make this 2 sine t cos t. It's minus 2 sine 2t. Minus 2 sine 2t. Minus I. How do you integrate sine square t, guys? Let's hope you don't have this evil thought in your mind that it's cos square t. I can see some of you have a mild grimace on your face, suggesting you were thinking that. How do you integrate sine squared? It's a trick. Let's use another way of formula. 1 minus cos 2t. 1 minus cos 2t over t. So it could be 1 minus cos 2t over 2. Minus the same here, 3 into 1 plus cos 2t over 2 t. I wonder if we can simplify that a bit. Yeah, perhaps. Let's try 0 to pi. This one is simple enough. Minus 2 sine 2t minus I. Here we would have minus 1. That's minus 1. Minus 1, yeah. Yes, that's right. Minus 1. And then it's minus half cosine, minus 1.5 cosine, minus 2 of cosine 2t. Minus 2 cos 2t. Now it looks a lot more manageable. And you know when you integrate cosine, it becomes sine. Plug in 0 to pi, it becomes 0. Remember this trick from the first chapter. You integrate cosine, it becomes sine. When you plug in 0 and pi, it will disappear. Anyway, let's do it. And now we are about to calculate this thing. If you integrate minus 2 sine 2t, what's the integral of sine 2t? Minus cos 2t. So it will be cos 2t. Yeah, that's it. Cos 2t. Here there's so many minuses here. Okay, let's leave it at minus. So here we have integral of minus 1 is minus t. Integral of minus 2 cos 2t. Integral of cos is sine. So this will be minus 2 sine 2t. Limits are from 0 to pi. Yes? Plus. Sine 2t. Oh, yes. 2 will cancel off. That's right, yes. You're right. Good. So now let's plonk in this limits here. So we'll get cos of 2 pi minus I into minus pi plus sine 2 pi. Subtract. Now plonk in 0. Cos of 0 is 1 minus I into 0 plus 0. Cos of 2 pi is 1 plus pi I plus 0 minus 1. So it's I pi. That's what we had from the previous method. It works. Which is an easier way of doing it. You have a choice between method 1 and method 2. Always when you choose method 1. I just did this entire thing to show you that because you have to do it sometimes. It won't always be as convenient as method 1. I see why it's so important to do the tough problems. Because you practice. When you go through the motions, you get to know what is involved, within the problem. You just read it, it doesn't help you. I'm worried also about those last couple of problems we did on the heat equation and the Laplace equation and the square. We didn't actually have good tutorials there because we had the unrest taking place and lectures were cancelled and disrupted. So I think, for this week's Monday is cut. Rather invest a bit of time in your weekend going through all those problems. Then on Monday you come to class and we can have a more productive TUT session. Otherwise we come to TUTs, I just sit there waiting for somebody to ask something, nobody asks anything. Nothing is learned and very few people turn up. It's not supposed to be like that. Don't make the mistake of saving up all the problems like for the test. Then it'll come down and be like a ton of bricks because there'll just be too much stuff. Do it systematically. And one last problem. By the way, the next test will be not exactly the same date, it will be the day before, it will be a Tuesday, during the maths period. So we managed to make both Mallersburg and coincide. We won't have that problem we had last time, 5 p.m. and stuff, confusion. 16th April. Well, it will be the Tuesday. I'll send out a bulletin. I'm just waiting for the Mallersburg lecturer to speak. No, it'll be a single. Unless you want a double period test. Then you'll die. It'll take me long. Single period is much safer. In any case, as I was explaining to somebody early on, a 25-mark test is roughly the pace of the examination. 25 marks in 45 minutes equates to 100 marks in 3 hours. That's why I made the marks 25. I actually made a mistake when I said 20. I adjusted it. Oh, so here's one more twist in the tail. Repeat previous, but with path from 1 naught to naught 1 to minus 1 naught. Okay, in other words, integral of gamma 2z plus z bar dz. The first 2 examples were the same problem, but using different methods. Now I'm going to use different paths. That's different. There's a whole new ball game now. If I use a different path, do you think I'll get the same answer for the integral? That's the question. This time the path is, you start off at 1, 0. You go in a straight line to 0, 1. And then from 0, 1, you go to minus 1, 0. Let's call that A, B, and C. And also, I should have said, let me say anti-clockwise here. Now, the anti-clockwise has to do with T. Which direction does T? The positive sense of rotation for angles is anti-clockwise. Here, we don't have angles. T is something else. Now, we need to parameterize. Do you think we'll get the same answer? In other words, are the complex integrals the same irrespective of which path you use? I wonder. It'll be quite intriguing to see. Let's see. Well, you see now there's 2 paths here. Now this path from AB, for example, right? Let's parameterize AB. The equation of AB is y equals to minus x plus 1. Or you can say x plus y equals 1. So as a parameterization, I can say let y equals to t, and x will be equal to 1 minus t, 1 minus y. That's a possible parameterization. There could be others. Don't try the trig ones, it won't work. Trig functions are circular functions. They work in circles and hyperbolas. Well, actually, hyperbolas have got cosh and sinh functions, not actually sine and cos. So now we need to work out what is the limit on t. What can we say about t? So the game starts here at 1, 0. What's the value of t at 1, 0? When x is 1, what is t? 0. When y is 0, t is 0. So at 1, 0, starts off at t being 0. And ask the same question at b now. So from A goes to B. When x is 0, what is t then? 0 equals 1 minus t. T equals 1. So t equals 1 here. So it goes from 0 to 1. The actual correct way to write it is to say that 0 is more than equal to t is more than equal to 1. 1 is less than equal to t. Actually, the other way around. 1 is more than equal to t is more than equal to 0. That boils down to 0 less than equal to t less than equal to 1. Actually, this is more difficult. T is bigger than 1. T is bigger than 0. Okay, so that's the first part. So we can say z equals to t plus, no, 1 minus t. 1 minus t plus it. That's x, that's y. dz will be differentiate this with respect to t, minus 1 plus differentiate t is 1. So it's minus 1 plus I dt. That's dz. How about the other part there, bc? Of course, here, bar z will be 1 minus t minus it. Now for BC, the equation there is y equals x plus 1. Or you can say x is equal to y minus 1. So if you put y equals to t, then x becomes t minus 1. The thing changes here. In fact, just to avoid lots of confusion, let's rather just write this here as it is like that, because I can now use this notation in this part here. So when x is 0, here x is 0. Put 0 here, what is t? T is 1. So the starting point is t is 1. What's the ending point? X is minus 1. Put minus 1 here. What is t? Minus 1 and minus 1 cancel to t is 0. So it starts at t equals 1 and it ends at t equals 0. That's why I think here it's better to say 1 more than equal to t more than equal to 0. That's a more sharper notation. Although it means the same thing. It's between 0 and 1 basically. But the direction, because of the anti-clockwise stuff, we have to go like that. So then z is x plus iy, so it's t minus 1 plus it. Obviously, z bar is t minus 1 minus it. And then dz will be, differentiate the first one, it's 1 plus I dt. Okay, so that's where we're going to stop because time is up. So can you please try to finish this if you like? Just substitute these in the calculation. There are two integrals to work out, two parts. Separate them and then add them up at the end. AB and BC are separate pieces of integrals.